Hi guys, hope all of us are doing great. My name is Ernest and this is Ernest Sciences and Mathematics TV channel. I'd like to welcome each and every one of us to my channel and kindly like to request us to subscribe to our channel and also engage us in the comment section. Now for this specific discussion for today, we are going to look at an extension of the concept of a decay series, or rather the decay process. And in our first two videos, or rather number of videos that we have done some aspect of the radioactive decay, we have mentioned that the decay process basically entails the concept of a release of energy, and this is accompanied by various range of products which we had mentioned in one way or another. And of course, for today, we're going to look at the aspect of decay energy, as we had mentioned as energy as one of the products of this radioactive decay process. So in this particular case, we're going to look at the concept of alpha decay, and in our subsequent videos also we're going to look at step by step of other processes, of course, and how we're going to be able to describe this specific energy that is released during the decay process. So in our last discussion, we have had a concept of what we refer to as the binding energy, and we basically give this specific initial for E subscript B in reference to the concept of binding energy. And in that specific discussion, I mentioned that basically we can be able to describe this concept of binding energy, which is analogous to the energy of formation. In normal chemical reactions, we come across concept of formation of various chemical species, and also there are some reactions which are going to involve the dissociation of various molecules in forming a range of specific products. So in that particular aspect, we say that it's going to involve the either the release or absorption of energy. And under the concept of binding energy, we say that this is basically in a nuclear reaction is going to entail the concept of the splitting of this specific nucleus, and therefore it's going to be accompanied by the release of energy, or rather the formation of this specific nucleus. And of course, this is basically the combination of the neutrons and the protons, which are of course contained in this specific nucleus, and therefore this is going to be accompanied by release of energy. Now, in our discussion on various thermochemical processes, we say that there are two specific kinds of description we can use for energy. Now, the release of energy is referred to as exothermic process, while the taking in of energy is referred to as an endothermic process. We use the positive and negative designation for these two specific processes. And of course, we said that this is for an exothermic reaction, we are going to use positive notation in order to refer to that one. And then for positive, this basically refers to an endothermic reaction. Now, in reference to this, of course, whenever we are going to talk about the concept of decay energy, in some cases, I'm going to use these two specific denotations for either release or uptake of energy in various nuclear reactions. So in our specific case for today, for the alpha decay, we're also going to see that the alpha decay is going to entail the mass transformation. And this specific change in mass, of course, it can be able to be described in terms of energy, in terms of the Einstein's energy mass relationship, which is given as the energy is equivalent to the product of mass of those specific particles, or the particle in reference, and the square of the speed of light, given as c. So in this case, as we said, basically we're going to emphasize on the concept of a change in mass, and therefore we can be able to give mass with this with respect to this specific equation for Einstein's energy mass relationship by halving the ratio of energy and the square of the speed of light. And as we said, for the nuclear reactions, we're going to give energy in terms of mega electron volts, or in terms of electron volts. We had spoken about a range of conversions that, of course, we were going to consider in trying to look at these specific conversions of energy. As we said, energy can be measured in terms of joules. So if we are going to use a reference for this specific conversion of energy, we can be able to give a dimension for energy, whereby 1 joule is going to be given in the units of kilogram mass squared over, or over the square of a second. So in another conversion, we're going to see that 1 electron volt as the units that I've given in this specific case for nuclear reactions is going to be equivalent to 1.6022 and the power of 19 joules given as such. So as well, we're going to see that there's going to be involvement of the concept of the molar concept, whereby we're going to involve the concept of Avogadro's number, basically which can be given as A. So we have said that Avogadro's number from our discussion of the mole concept is equivalent to that specific number, which is 10 to power 23 particles as a product of 6.022. And then we're going to, I've mentioned about the concept of a speed of light. So this is going to be given as this value, kilometers per second, given as such. So this can be converted into the standard units of, so basically it's going to be given as 10 to power 8 meters per second in some of the literature that we're going to see. And lastly, we're going to look at the concept I've mentioned about the concept of mass. So we're also going to use a conversion of 1 atomic mass unit. And from the subatomic particles we have discussed in our introduction to radioactivity, I mentioned about the constituents of the nucleus or the subatomic particles, which entail the electrons, protons, and neutrons, and we had given their various masses and of course the charge and other aspects of their characteristics. So this is going to be equivalent to 1.66 times 10, and this is a negative 27 kgs or kilograms, and this is going to be equivalent to 1 atomic mass unit. So therefore, whenever we give a reference for the proton as equivalent to 1, the neutron equivalent to 1, and perhaps the electron having a ratio of maybe 1840, the reciprocal of 1 over 1840 given as such. So this is equivalent to 1 mass, 1 atomic mass unit, 1 atomic mass unit, and these are a fraction of the atomic mass units. So therefore, this one arm is going to represent 1 atomic unit in this specific discussion. And therefore, lastly, for this specific comparison of energy, we're going to use a specific ratio for this mass, whereby we're going to have 931.46 given as such. This is going to be mega electron volts, of course, over c squared. So basically, this is going to be a constant for 1 atomic mass unit we are going to use in reference to describing this mass over this specific decay energy that we are going to use in our specific discussion. So going forward, therefore, having discussed about the various aspects of the concepts we have learned before in relation to the decay energy, I'm going to just give an illustration of the general description for the alpha decay that we had given in our first discussion, whereby we say that we can be able to represent the alpha decay using this general representation for an atom for mass number and the atomic number given as such. And we're going to see that this particular process is going to involve a transformation whereby the mass number is going to reduce by 4 for the alpha particle, and the atomic number is going to reduce by 2 in this specific respect. And this is going to result to the formation of an alpha product or an alpha particle that is going to be represented as the helium nucleus given as such. So in this case, of course, we are going to see that for the alpha decay, in order for us to describe the energy that is going to be involved, we're going to see that this is going to be experienced particularly for elements that are heavier than lead. And we're going to see that a few of the nucleus that are going to be lighter, especially in the lanthanide series, are going also to be experiencing this specific kind of decay. Now, for the lead element that I've mentioned, of course, we're going to see that this particular range of elements which are heavier than lead, we can be able to give a description for this for the mass number and the atomic number given as such. So this means basically that these are going to be elements which are going to be heavier. Perhaps a range of elements we can describe as E, or rather maybe just give them as X, which are going to have a mass number greater than lead. Of course, they're going to undergo this specific process of the alpha decay. Now we can be able to describe the energy that is going to be associated with this specific type of radioactive decay by considering the change in mass that I've mentioned, and also of course the specific atomic mass, the specific energy that is associated with the one atomic mass unit, which are referred to as a ratio between this specific constant for mass for that specific particle and the constant which is a speed of light given as such. So therefore this is going to be given, this ratio is going to be given in terms of mega electron volts. Therefore we're going to see that the decay energy that is going to be calculated for the this alpha decay is going to be calculated from the atomic masses that we have mentioned. And this is basically because we had talked about the concept of binding energy which is released, and therefore this binding energy was corresponding to a change in mass, whereby we had given a general representation for the binding energy as equivalent to, so this basically was in mega electron volts, and we had decided that this binding energy is equivalent to, so as I had said earlier, the negative sign is going to imply the release of energy. So this is going to be equivalent to the product of this specific one atomic mass unit given as such, and then changing the mass of that atom as well given in terms of atomic mass unit as such. So this particular value was going to be given in terms of mega electron volts, as I've said in my previous mention in this specific discussion. And the energy that is going to be associated with this, of course, kind of decay is going to be referred to as the Q value of the reaction. And therefore, proceeding forward, I'm going to use the concept of the Q value of this specific type of energy. So for us to illustrate this mass that is associated with the alpha decay, we're going to give it in terms of the Q value in mega electron volts, which is going to be equivalent to negative 931.5 times the change in mass given as such. So if we try to look at this, we can be able to, of course, this is a constant, and this energy is going to be given in terms of mega electron volts. So what we are going to be after in this specific case is the change of mass. As we said, the change of mass is going to be associated with this specific energy, or is relatively direct to the or proportional to this specific type of energy. So as we normally do for our normal chemical equations, whenever we are trying to find the energy, it's going to be the difference between the product and the reactants. So it is the energy of the product and the reactants given as such. So we're going to give the difference in mass in terms of this specific product and the reactants given as such. And that change in energy is going to be give us this aspect of the Q value. So if we try to look at a specific example, we can be able to look at the isotope of uranium-238. So this is a capital letter. So we're going to have uranium-238 undergoing the alpha decay and leading to the formation of thorium-234 plus the helium, which is going to be given. I'm just after the mass numbers because, as we said, this basically is going to be an aspect that is going to entail how heavily rely on mass. So therefore, we're going to be after the mass numbers. So if we we look at this, given that the mass of this uranium-238, so we can be given a particular value for 238.050. So this is a given value. We are not going to be so much concerned over what it is. We'll be given a specific quantity for that, and the mass for basically we can be able to look at the mass for helium as well. It's going to be 4.00, and that is 2603. And then we're going to have the mass for thorium as 234 point. So this 0.0435994. So for us to find the Q value, which is basically going to be the decay energy in this alpha decay process, we're going to do away with this so that we can use this space. So for us to find the Q value in mega electron volts for this alpha decay, we're going to have it given as negative value, which is a release of energy, 931.5, which is this is a mass for one atomic mass unit in mega electron volts, and then we're going to have this one as a product of change in mass. So the change in mass is 234. As we said, it's a product minus the reactants, 0.43594, and then this is going to be, so the product of the two masses I've written for this one thorium, and I'm going to add the product, the sum together, the 2603. So these are the products which are going to be formed, and then I'm going to minus the mass for the reactants, which basically in this specific reaction is going to be uranium-238. So its specific mass 238.0507785 given as such. So the difference in this, or the product of the two, is going to give me a 4.27. This is 4 mega electron volts as the Q value of the alpha decay in this specific case. So again, as I've said, this is the process that is going to assist us try to quantify this specific kind of radioactive decay in terms of energy, whereby we said we have various radioactive decay processes, which is alpha, beta, gamma, positron, and then we have a negatron emission and other electron capture, etc. So specifically in this particular case, we're going to look at the alpha decay, whereby we say that alpha decay entails the release of a helium nucleus, or the formation of a helium nucleus from the target, perhaps from what we can be able to refer to as the nuclear equation. In this case, we had mentioned the concept of a projectile and target in reference to this, which was going to form other products like the recoil and the product in our first discussion, in general discussion of a nuclear reaction. So in this specific case, we are going to consider uranium as of course, a target that's going to be, of course, involved in the release of a helium nucleus, and these are the product, which is a daughter, of course, daughter nucleus, which is going to be formed from this. So therefore, we are going to consider the change in mass that is occurring between the product and the reactant, or rather the product and this specific reactant in quotes. As I say, we can be able to compare this to a normal chemical reaction. So we're going to find the difference between this one in terms of mass, and the difference between that and this specific product for one mass or one atomic mass unit in terms of a mega electron volts from Einstein's energy mass relationship is going to give us what we refer to as the Q value of this specific decay process that we refer to as alpha. Now this one, in collaboration with others, we're going to see that it's going to assist us find a way of describing these Q values for various radioactive processes apart from the alpha one that we have done in this specific video. So catch us in our other videos where we're going to look at various other examples, especially on the other radioactive decay processes that we have already discussed in some of our videos. Kindly check on our link of our description boxes below so that you get a list of other videos which are related, which are going to assist us, of course, to comprehensively understand these various aspects in radioactive decay processes. So that is it for now, guys. Bye. God bless.